we can get fossilized samples of protoplanetary disks, in particular our own solar system. And this is a sample of a carbonaceous chondrite called the Allende carbonaceous chondrite. If you crack them open, you find things like chondrules, which have been their small silicaceous spheres about 1 millimeter in diameter. And then you also have calcium aluminium inclusions. Both of these particular objects have been heated to high temperatures, and they're surrounded by matrix material. Oh, the CAI is some of the oldest subjects in the solar system, about 4.6 billion years of age, and they're surrounded by, and chondrules formed some millions of years, contemporaneously with CAIs and also millions of years afterwards. And the surrounding matrix that binds all this material together is made of processed material. And all this is an assemblage of basically igneous objects that have been cemented together under relatively low temperatures, probably in the outer solar system, and at temperatures below 500 degrees Kelvin. So we have this material basically that's formed at high temperatures, but locked together in low temperature material, if you like. So how could this be produced? Well, there are two general forms of theories. There is the local formation theory, where the material was actually, all this was produced, heated up and produced and cemented together in a particular region in the protosolar disk or other protoplanetary disks. Or there's a non-local production theory, where you have materials produced near the star or the sun, where most of the energy is, and it's ejected out or transferred out by turbulence by radial transfer. And so there are basically two. The meteorologists tend to favor the non-local formation, the local formation idea, while the astrophysicists tend to favor the non-local formation idea. But probably it's a combination of the two, at least in the early solar system and probably in other protoplanetary systems. So this is a busy graph, and it shows some information about CAIs. Remember, that's the first material that condensed out in the solar system, those white irregular objects I showed, part of Allende. And in this particular graph, you can see this is a graph of oxygen isotopes, O16, O17, O18. And one section of the graph shows oxygen 16 poor. It's down the bottom. Oxygen 16 poor is up the top and also on the right-hand side. Oxygen 16 rich is down the left-hand corner. And so the planets, for some reason which we don't understand, probably to do with water processing in molecular cloud, the nascent molecular cloud that produced the solar system, those are O16 poor. But the sun, which was measured by the Genesis mission, is O16 rich. And the CAIs are on a mixing line between the two of those. And so that's partial evidence. There are other lines of evidence that suggest that the CAIs were actually formed near the sun and then radially transported out to where the meteorites were formed. Chondrules, which remember those small silicaceous spheres, they were probably produced local formation, where you had planetesimals coming together and the jet of liquid that came out. Then the gas interaction with the liquid, molten liquid, produced these small silicaceous spheres. And some evidence for that are things called cluster chondrites, where you have the chondrules all sort of formed simultaneously. They were semi-molten when they formed. They aggregate together and they're embedded. They've sort of formed into each other. Some were hard, some were not. And so that's evidence for local formation. There are other elements of evidence for that as well. Non-local formation, we have more evidences from the Stardust mission, which was some years ago, which sampled dust grains from comet Wild 2. And that was from a comet that formed approximately, it's thought, 40 AU. And when all the dust grains, which were captured by these aerogel mitts, if you like, all the dust grains that were obtained from that mission were refractory, were formed at high temperature. And they were basically samples, again, of our old friends, CAIs and chondrules. So these things were formed at 40 AU, and you still have the same general pattern where you have igneous, high temperature material, but in this case, not surrounded by stone, but by actual ice. So it's in this fire and ice scenario, which we again see repeating. So we can see that this material was radially transported out to the outer regions of the solar system. If we look at other stellar systems, this comes from X-Lupi Spitzer Space Telescope observations, where there was a starburst which transformed the amorphous dust grains around X-Lupi to forsterite, crystalline forsterite. It's a magnesium silicate oxide. And this is just a schematic of what happens, a 10 micron feature The blue line is the amorphous 10-micron feature, but then after the starburst in 2008, it produced these crystalline features that basically force-derived features. So again, we see that amorphous dust can be converted into crystalline dust as a function of the starburst activity. So this looks at more material from X-Lupi. You have the starburst occurs in 2008. You have these force-derived signatures on the 10-micron feature. As time progresses, the silicate features move out. They move away from X-Lupi, and they go into longer wavelengths. And you can see this modeled on the right-hand side, where you have this outward wave of dust that's traveling out at approximate speed of around 20 kilometers per second. So these things are really moving along. And eventually the signal disappears. Perhaps the dust grains went back into the disk, or perhaps they lowered in temperature so it couldn't be detected anymore. Another example, I won't bore you with too many more examples, but this is HOP 68, which is a protostar in sort of the Northern Orion section. Again, using Spitzer Space Telescope, people looked at the dust grains around the protostellar system, amorphous dust grains, but nearby in the near region, they were again force-derived silicate. Presumably, the authors suggested that they were produced by outflows, produced near the star, ejected back by outflows, and they called this olivine or crystal rain falling back onto the protostellar system. So some years ago, in conjunction with an academic here, Michael Brown, when he was a student, and some years ago in 1995, we did an experiment, just a simple numerical experiment. Michael was doing his honours thesis at the time. And we basically had a star, we had a disk, not shown to scale, and we ejected the particles that were in Keplerian rotation around the star, and we eject them out at particular speeds. And we made the prediction, we published a number of papers, and we made the prediction that we would expect outflows ejecting out material from young stellar systems. And that prediction, as you saw, was actually confirmed with the Spitzer Space Telescope. Sorry again for this banner that's up there. And so you can see in the first section, you have the disk at the bottom, you've got Z, you have the particles ejected out. If you've got particles close to at the escape speed, which is a lower curve down there, you can see it's just at faster ejection speeds, you're going out vertically. In B, you've got basically looking down, plan view of the disk, its particles are in Keplerian rotation, they just get ejected out into rectilinear motion. Basically, your angular velocity decreases. Your angular momentum remains the same, of course. And the bottom section, you've got radial speed. The initial vertical speed gets ejected out and turns quickly into radial speed. And the speeds at the escape speed, and at lower speeds, we get speeds that are consistent with observations. So this leads to the theory part, if you like, that if you have the model where you have particles ejected out from the inner parts of the disk, they have low angular momentum relative to outer parts of the disk. And so if you have homogeneous infall of particles onto the disk, what you'll get is gap formation. So basically you have low angular momentum material going into high angular momentum disk sections. And so you're going to have radial infall of material, and you basically get it. Particular sections, you'll get accretion, and they'll form compressed regions, high density regions. And on the other side of the gap, you'll have dust trap, which will also be placed. So if we have a look at a bit of the mathematics, what we've seen for protostellar systems and what we heard yesterday from one particular talk, that protostellar systems don't seem to show much viscosity. So if we look at mass conservation, the angular momentum conservation equations, but in the inviscid form, and so we have disk surface density, radial infall disk speed, and then we have this rate of infall disk surface density. This is the infall material falling onto the disk, and you can do the same with the angular momentum. You can solve these equations analytically to some extent and show you've got a radial accretion speed, if you like, that's just simply given by that quantity. And you can also do a mass accretion rate just by the standard means. And so you get disk accretion without viscosity in small sections of the disk. So you can combine these two terms, and that gives you basically a master equation for disk evolution for infalling material. And you can solve them for simple cases where if you have material has zero angular momentum approximately, and over a section of the disk you have constant rate of infall, you can solve these equations. That the master equation goes to that simple equation, and then the radial infall equation goes to, again, another simple equation. You can solve them analytically for the position of the disk and also the surface density of the disk. And that tau G is the gap formation timescale. And when you put in semi-reasonable values for the gap formation using this process, you get quite fast gap formation, about 100,000 years. Of course, you can tweak the numbers, it can be shorter, it can be longer, but semi-reasonable number, 100, 200,000 years. So this could be a formation mechanism of gas for prostellar systems, and what would be the, at least very quick timescales, and what would be the implications of this? You have material in the top picture, you've got material coming in, it's processed, hot igneous processed material, forms a compressed region, high density region, on hopefully relatively short timescales. And so if you look at the surface density concentrations, just putting in some numbers there, you can get concentration, surface density concentration increases of an order of magnitude or more. And if you look at the amount of material that's going into these crush regions, these compressed regions, it's going to be processed material. And so that means that that what's coming in here in terms of this high density region, most of the solid material is actually going to be igneous process material. So if you look at a gap ratio, the outer gap radius divided by the inner gap radius, if it's 1.1, then you find that 70% approximately of the material in that high density region, which could form planetesimals, is actually processed material. So in summary, what does this actually mean? If you have for the solar system and also protostellar system, you can have the disk winds, the high velocity jet flows, are pumping out these O16 rich CAIs, these calcium aluminium inclusions, and the sort of nominal disk winds from the inner disk putting out this forced-right dust, which again, this is what we observe in one way or another, directly or indirectly. That could fall onto a disk, it's low angular momentum material, and it can form gaps in the disk at relatively short timescales, and the planetesimals can form in two regions, basically in this high density layer, or where this other gap is, where you have pressure differential, which make it a dust trap. So that's the end of the talk. Sorry for the technical problems. I welcome any questions. Thanks for your attention.
Hey, really interesting talk. I was just wondering how, like, whether this mechanism can explain like many concentric rings, and like, I'm not sure whether I just misunderstand, but why would the material fall on just like at one particular radius to open a gap rather than being scattered?
It would be totally random. You couldn't predict it. So it could form multiple times. You know, you could have stochastic formation of these gaps. So you can't actually, unless you have a proper model of, you know, the gas and the outflow and everything else, you can't really predict where it's going to fall. Some material will just be simply ejected out. I don't know if that answers your question. Totally random.
Thank you.
And will the next speaker make it start getting set up? I just have one question, a naive question, but are there any plans to look at all the data? I know you mentioned a bunch of observations at the beginning, but
well, if there are any students at Monash University that want to look at that, that'd be great.